Hi guys, welcome back to Nitronics, and today I've partnered with AMD to talk a little bit about their 7 series lineup of FPGAs. Of their entire lineup, the 28nm 7 series FPGA devices have been AMD's most popular series to date. With that expectation of knowing that their customers rely on their 7 series based products, and those life cycles are a little bit longer than a lot longer in some cases, than the typical industry standard life cycle of 15 years, AMD decided to extend the product life cycle of their 7 series devices, all temperatures, all speed grades, through at least 2035, which is super exciting for several reasons to both hobbyists and industry professionals alike. Because as engineers, we all know there's nothing more frustrating than finally figuring out how to use a certain tool or device, integrating it into your product, getting through to production, and then it finally goes obsolete on you at the last moment and having to basically do everything over again, interrupt your production, relearn a new upgraded tool. That's why this is a pretty big deal that they've decided to extend the lifecycle support. So today I figured I would take a look at the different devices in the 7 series lineup, kind of explain the differences to you and why I choose different chips for different applications. Let's get into the lineup. Now there are 5 different product families in the 7 series lineup from AMD. That includes the Arty A7, the Spartan 7, the Kintex 7, the Vertex 7, and the Zinc 7000. And the main point behind having these 5 different product families within the 7 series lineup is to cover every user need all the way from lowest cost, lowest footprint, all the way up through highest system performance. Starting with the Spartan 7 on the lower cost optimized end of the scale, eventually leading up to the Vertex 7 for your highest system performance needs. Now, some of the 7 series devices also have UltraScale Plus siblings that even up the performance more. But we'll take a look at a couple of the UltraScale counterparts a little bit later, but for now, let's take a look at some of the main players in the 7 series family here. Now, from personal experience and personal preferences, when you ask me my top choices in the 7 series lineup, that's gonna be the Zinc 7000 system on chip and the Arty A7 chip. I really like the Arty A7 chip because it has come through for me in a lot of my lower cost constraint applications along with lower power constraint. And then the Zinc 7000 with that physically instantiated ARM processor in the programmable logic of the FPGA is just, it's like my Swiss Army knife when it comes to FPGAs. I'm very attached to it. Taking a step back from my personal preferences, just to talk a little bit specifically about the high-level differences between the 5 different product families within the 7 series lineup, let's talk about the Spartan 7 first. The Spartan 7 is, like I said, it's the lowest cost for the max performance per smallest package. So not necessarily that it is the smallest package, but it is the highest performance for the smallest package, if that makes sense. It also has the best trade-off for user I/O pin count compared to cost. So if low cost and as much I/O as possible is the top 2 things on your list, you're gonna wanna choose the Spartan 7 chip. Taking a look next at the Arty A7 chip, the Arty A7 chip is the best trade-off between highest transceiver speeds as well as DSP bandwidth and lowest cost. So the Arty A7 was my primary candidate for a industry project where I had to create a small, handheld, battery-powered, software-defined radio device. Next, looking at the Zinc 7000, like I mentioned, it stands apart from the rest of the devices in the 7 series family because it actually has a physical ARM core processor built into the programmable logic. So if you have some sort of application where you actually need some sort of CPU type processing application, as well as some sort of HDL design in the programmable logic, the Zinc 7000 is gonna be your choice for that because instead of having a separate processor and a separate FPGA on your PCB where you're gonna have some latency loss in between, it's all in a single chip. And another great application example of the Zinc 7000 is Tektronix recently released a entry-level oscilloscope that was solely based on the Zinc 7000 as its brain to accomplish all of the signal processing, handle the timing that's required for taking measurements as you would need to on an oscilloscope. Next we have the Kintex 7 and the Vertex 7. These guys are on the upper end of the performance spectrum, and this is where you're crossing the line of you don't care about cost as much as you just need the performance. However, the Kintex is the absolute best balance of the entire 7 series lineup between cost ratio and absolute maximum performance from all aspects, whether it's number of I/O pins, logic cells, transceiver speeds, all of that. And then finally, your Vertex 7 is your heavy hitter. That's what you bring in when you just absolutely need top-of-the-line system performance. There are some industry standard radar applications that use the Vertex 7. So really, the Vertex 7 is your top-of-the-line sports car of the 7 series lineup when you need the best you can get. Now that I've given kind of a high-level overview as to what you would use the different FPGAs in the 7 series lineup for, I thought it would be fun to do some practical demos, really comparing some of these chips as head-to-head as possible. Which is why I've picked up some of the development boards such as the Arty A7 and the Arty Z7. The Arty A7 is an Artix-based board, and then the Arty Z7 is the exact same development board, just Zinc-based. And I've created projects for both so that you can see exactly how much more power the physical ARM core processor in the Zinc's gonna pull compared to a purely RTL design in the Arty project. Furthermore, with the Zinc chips, there's also a dual-core ARM option and a single-core ARM option, which is why I have my 2 Zinc berries here, which if you followed Tektronix for any amount of time, you know this is probably my favorite FPGA. But I've created bare bones applications for these so we can really just compare the chips side to side, exact same hardware, exact same setup, and you can get an idea of when it's best to use which one. And like I mentioned earlier, I have a couple of the ultra-scale options so we can really compare the power draw and performance differences. I have both a Zinc ultra-scale option here and an Artix ultra-scale option. So let's take a look at a couple of these projects in Vivado using the analysis tools to kind of get a base idea of what's going on between these different chips. Alright, so starting with the 2 Arty boards, I have created a bare minimum boot up design with the base peripherals for both boards. So I have a microblaze instantiated in the Arty A7 project to connect all the peripherals, and then I have the Zinc processing system to connect to that physical ARM processor in the Zinc 7000 chip. Now, as you'll probably notice in the Artix-based project versus the Zinc-based project is it looks like there's a lot more connected in the Artix-based project compared to the Zinc-based project. This is because one of the perks of having that ARM core processor in the Zinc 7000 chip is that you have direct connections from the ARM core processor to peripherals such as Ethernet, UART, SPI, all of that stuff, so you don't have to route them through the programmable logic and make all of those interfaces by hand, whereas with the Artix-based chip, you do need to instantiate IP manually to make all of those connections. So you can think of it as you have direct pins on the Zinc chip that connect straight to the ARM core that don't go through the programmable logic. But you do also have pins that go through the programmable logic on the Zinc chip as well. So you really have the flexibility to do whatever you want on the Zinc 7000 chip versus some of the more manual work you might have to do on the Artix-based chip to accomplish the same thing. However, if we take a look at one big thing, which is the key difference, let's look at the overall power draw of these designs, which again, these are just the bare minimum designs needed to boot up both boards and have a fair amount of the peripherals available. And as you can see, the power draw is quite drastic. We're only drawing a little bit less than 1/4 of a watt on the Artix-based Arty board, compared to 1.5 watts on the Zinc 7000 board of the exact same design, exact same peripheral connections, the only difference being the Zinc 7000 versus the Artix brain. That's kind of the first demonstration of you have an easier time hooking things up on the Zinc 7000, you have more CPU processing, however, you're drawing a whole lot more power as a penalty. Now that we've looked at the difference between an Artix chip and a dual-core Zinc chip, let's take a little bit closer look at the Zinc 7000 and compare a single-core Zinc chip with a dual-core Zinc chip. Now you'll probably notice that these two designs are drawing the exact same amount of power at 1.3 watts. This is because the base design on both of these and the Arty Z7, I only have one of the two cores programmed and working in these designs. However, you can take advantage of both cores at the same time and have them running at the same time, which would cause your dual-core Zinc to start drawing a little bit more power. But I did want to demonstrate that at its base, if you only have one core of the dual-core Zinc working, it still matches the single-core Zinc chip. Which, if you're looking to save money and you know you don't need both cores of the dual-core Zinc, go with the single core. It's a great way to cut down cost on your project if that's a high concern for you, but you still need the processing power of that physical ARM core. Now that I've looked at both of the Zinc 7000 options, that's where I wanted to bring in and compare how is this different from its ultra-scale counterpart, the Zinc ultra-scale, which I have the brand new ZU board here, which I've created another base project, bare minimum boot with bare minimum peripherals, just to really showcase the Zinc chip itself. And as you can see, this particular chip with this bare minimum design is actually drawing 1.2 watts, so a little bit less than the Zinc chips on the two Zinc berries. However, the key difference of the Zinc Ultra Scale compared to the Zinc 7000 is you gain a real-time processor, or a few real-time processors, in the Zinc Ultra Scale Plus, and you also gain a GPU in the Zinc Ultra Scale Plus. So if you need a lot of graphics processing or more heavier video applications, that's where you're gonna want to step up from the Zinc 7000 to its Zinc Ultra Scale sibling. So even though I use the Vivado analysis tools to look at the predicted power draw of the design, I thought it would be a little bit better to actually look at what the devices are going to draw with a simple Hello World application running on each of them. So I picked up one of these little USB sniffer devices that tells you how much power and voltage or how much current and voltage you're getting across the USB, and we're going to use Vitis to actually deploy a Hello World bare metal application on both my Arty Z7 and my Arty A7. And up first I have my Arty A7. So at the moment it's just powered on. I don't have any application running on it. I don't have the programmable logic programmed in any way. We're at 5 volts and 0.2 amps just over the USB UART JTAG port. Let's launch a debug run. So I'll launch on hardware from Vitis. We'll give that a moment. And then now that I've entered the main breakpoint, I've got a loop in here that will just indefinitely print Hello World. So let's just go ahead and run that and see what our power draw is. And it looks like we're holding steady at our 0.21 amps. So let's switch over to the Arty Z7 and see how it compares. Alright, so I've got the Arty Z7 plugged in, and on initial power up, without the programmable logic of the Zinc 7000 program or anything running on the ARM core, we're also sitting at 0.23 amps and 5 volts, which is the USB voltage standard since we're going over the UART interface. And I'm going to go ahead and launch the same Hello World application, just in the Vitis workspace for the Arty A7. As expected, with the Zinc 7000 running the same Hello World application, just printing Hello World indefinitely, we are at the same 5-volt standard, but we're running at 0.31 amps instead of the 0.21 amps that the Artix chip was drawing. So we've just verified what the Vivado analysis tools was telling us, but we did double check it with actual software running on the chips and not just the hardware design that Vivado was telling us. Let's move on and take a look at some of our beefier counterparts with the UltraScales. I have the ZU board here with the Zinc UltraScale chip on it, and I definitely didn't realize that my little power sniffer didn't allow me to plug into the serial port ahead of time, but I don't think it's really worth much just running the same Hello World application on the Zinc UltraScale, because just like we saw with the dual core versus single core Zinc 7000 on the Zinc Berries, because this Hello World application isn't taking advantage or activating anything that's different on the Zinc UltraScale chips, such as that real-time processor or the GPU or any of that, the power reading is going to be exactly the same way that the Vivado tools told us that the base design was actually going to draw a little bit less power than the dual-core Zinc 7000 on the Zinc Berry. But to show you what the extra power draw was going to be with something taking a little bit advantage of the extra hardware available in the Zinc UltraScale, I went ahead and created a PetaLinux image, which I've put on the SD card in this. So that'll show you what the Zinc UltraScale is going to look like with a full-blown OS running on it, which is probably what you're going to do if you're upgrading to the Zinc UltraScale to begin with, because you really do want to take advantage of the extra hardware in the Zinc UltraScale Plus. Let's go ahead and boot this guy up. And like I said, we'll have to wait a couple minutes because I can't see the serial output. That's okay, because we're just looking at power draw. And the ZU board, there's an extra step we do need to hit the power button. So on initial boot up, the Zinc UltraScale Plus, this guy's running on 15 volts, and during the initial boot up process, we're still looking at 0.36 amps, but I know for a fact it's not fully booted up yet because it just hasn't been long enough. So let's give that a moment. While we're waiting for all that, just to make note, all of these base design projects that I've created for all of these boards, including the PetaLinux images, which I've also created Linux images for the other boards as well, I'll have links to all of those blog tutorials down below. The only exception being is the base design to boot the Artix UltraScale is the exact same as the Arty A7, so you can apply those same tutorial steps to the Artix UltraScale. I didn't think that was worth another write-up just because it's the exact same steps, just targeting the Artix A7, but I will be writing blog posts that are unique to my Artix UltraScale board, which happens to be the XEM8320 from Opal Kelly, so I'll be getting into some more details with that in some future blog posts. Coming back to this guy, now that we've given him some time to boot up, and we just have PetaLinux running at its base, we are looking at our same 15 volt standard and about 0.34, 0.35 amps. And let's see what happens when we give it an internet connection. So we'll let that auto negotiate for a second, but I can already see we've jumped up from about 0.34, 0.35 to 0.39 amps, 0.4 amps, so almost half an amp. So that kind of gives you an idea. The more peripherals you have in the design, you have active, that's all going to add to your power budget. Taking a look at this, this also brings up the next segue, as we've kind of gotten an idea of the difference between running a bare metal or no OS software application on the ARM core versus a full-blown Linux OS. You can see that there's a pretty big power difference there. that same thing is going to apply to the Arty chips. Now, personally, I feel like if you do need a full-blown OS like Linux, 9 times out of 10 I'm going to tell you to go with the Zinc 7000 chip. Again, that comes back to things like there's an SD card interface already physically built into the Zinc 7000 in a way, so you just have to make sure you connect the pins to the Zinc in that way, whereas you do have to instantiate an IP in the Artix or Vertex or Kintex or any of the other just purely programmable logic FPGAs in the 7 series. You do have to instantiate the SD card interface manually on those chips. Xilinx does offer an IP for that in their IP library, however, I think it's still a part of the paid license. It's not in the free licensing yet, so a lot of the times, just for ease and less cost, I highly recommend going with the Zinc 7000 chip or any of the Zinc siblings, such as the UltraScale. Go with those if you need a full-blown OS. If you need to stick to the lower power, go bare metal on one of the Spartan or Arty A7 chips. So since getting into a little bit of the differences between running a bare metal application versus a full-on Linux OS on the Zinc and Zinc UltraScale devices, I went ahead and came back and wanted to talk a little bit about running an OS on the Arty A7 chip. So I have my Arty A7 here. Like I mentioned, running a full Linux OS on Microblaze isn't usually my first choice. I don't have necessarily anything against it, it's so much easier on the Zinc chips. But when you do run it on the Microblaze, the same way that there's a lot more manual configuration with the Microblaze chip to all of your peripherals, since everything has to be done by hand, there's a little bit more manual configuration that has to be done to the Microblaze. So the Microblaze design that you do in Vivado for a bare metal application is not going to be the same that you do for a Microblaze design in Vivado that you want to run a Linux OS on. Again, I have 2 separate tutorials that are written up about that because that's way easier to read about than listen to me talk about for a really long time. But ultimately, that's going to have the same impact of you're going to draw a lot more power running a full-blown Linux image versus just your bare metal application. So I've got that booting at the moment, and just during the boot process it looks like we just powered up the kernel and we're already at 0.43 amps just booting up for the kernel compared to our 0.2 amps that we had for running our Hello World application. So I'll continue to let that boot for a minute. Going back to the differences of having to hand configure everything on the Artix chip with the Microblaze compared to the Zinc chip, which again, that's why I think it's just a lot easier to use the Zinc 7000 chip, because from a hardware design perspective, you can use the exact same Vivado project for a Zinc design, whether you're running a bare metal application or a Linux operating system. They're gonna be exactly the same, whereas as you can see with my tutorial write-ups below, I have 2 completely separate designs for a bare metal design and a Linux OS on my Artix chip. And those same principles are going to expand to the Kintex, Vertex, or the Spartans as well. The other thing about running a Linux image compared to your bare metal application is you're going to have a little bit longer boot time, obviously, since you have a whole operating system that's coming up. So that's another design consideration if you're deciding, do I need a full OS for my FPGA design, or do I just want to go with a bare metal application if you're running more than just your HDL in programmable logic. Okay, so now that we're fully booted up with Linux here on our Arty A7 board, let's take a look. And it looks like we evened out at just under half an amp at 0.42 amps. So that gives you a better idea of the difference between running no OS bare metal on a Microblaze versus beefing up your Microblaze and running a full Linux operating system on it. As one final step, I do want to take a look at the Artix 7 sibling, the Artix UltraScale Plus, and let's see how much, if any, extra power the Artix UltraScale draws running the same bare metal Hello World application as we ran on its Arty 7 counterpart. So let's take a look at that. Alright, so I have a basic bare metal Hello World application up and running on my XEM8320, which is my Artix UltraScale board. And while I expected it to draw around the same power as the Arty 7, since I'm running the same software and I'm utilizing the same resources with my design, it's actually drawing about twice the amount of power at rest. So to give you an idea, I have the extra processing power of the UltraScale in that Artix chip, but I am drawing some more power compared to the base Arty 7 in the 7 series. I'm glad I ran that experiment. That wasn't necessarily what I was expecting, but like I said, typically you choose the Arty 7 when you're looking for that trade-off between cost and transceiver speed, as well as DSP bandwidth. And if you look at the direct comparison between the Arty 7 and the Artix UltraScale, one of the main upgrades you're going to get is the DDR3 on the Artix 7 versus the DDR4 on the Artix UltraScale chip. So that was a nice little comparison, and I think that kind of wraps up my exploration of baselining all of my 7 series chips. This was very interesting for myself. I saw some things that I expected, some things I didn't. Like I mentioned, this is how I go through and choose the best FPGA for my project. I hope this kind of gives you some more insight and helps you see what the different use cases are for the different 7 series chips from AMD and how to pick the best chip and setup for your specific needs. Let me know what you think in the comments below, and thank you again to AMD for sponsoring this. It's really great working with them, and I hope you'll stay tuned for the next videos on my channel. Bye!